Good morning. Happy after the holidays. This course into general relativity and cosmology. I am not Safir, who is the usual lecturer. He'll be here from next week. He's away this week, so I'm replacing him today and on Thursday. Tutorials will also be given by the usual lecturer. So we're not going to distinguish between lecture time and tutorial time. Occasionally there will be tutorials at the usual slots. So 2 sessions a week, Sunday and Thursday. The grade is 80% final exam, 20% homeworks, which will be given almost every week, maybe not this week, but almost every week. The homeworks are mandatory, and it's not that they're mandatory for your grade, it's that if you don't do them, you will no doubt fail the course. General relativity is not an easy subject. It's a very profound subject. There's a lot of mathematical depth and a lot of physical depth. And we're going to try to balance between the two of them. If you lose out on either one of them, you're hopeless. So come to class or watch from home if you can't make it physically. Do all the homeworks. Do them on time so you don't get out of touch and out of sync with the course, because every class will build on the previous ones. If you need for any reason an extension on the homework, email Asaf and ask ahead of time. Email sent after the deadline will be summarily ignored. Make sure you have enough time to do the reading, repeat the class, do the homework, follow whatever goes on. It will all be necessary. The syllabus, which appears on your Lambda site, includes a list of books. It is recommended to use at least one of them. Different books cover different parts of the course, and they aim at different levels. So try to find whichever one is good for you, or start with the basic one and then move on. The classical books include a book by Steven Weinberg. They're all called Gravitation or something like that. This is Gravitation and Kosmology. This is a 1972 book. So one of the old ones, one of the main textbooks of the course. It's good on experiments, on astrophysics. A bit heavy in mathematics. We will try to be a bit lighter, but it's a good one to start. So use it. The next one is Hartle, Gravity, an Introduction. This is newer, 2003. The second main textbook. This is highly recommended if you get confused. Less mathematics, more hand waving, but it gets the points across. So if you don't know why we're doing some mathematics, you can use this book to try to aim yourself in the right direction. Sean Carroll is the next one, Space-Time and Geometry. Again, an introduction to general relativity. Another one from 2003. This is considered a standard textbook in many places. So it does a great job in giving the proper amount of math and physics and balancing them. Sometimes it delves a little deeper, but a good place to look. Okay, 2 more books, or 3 more books. There's Lightman, Price, and Tukolsky. This is a problem book. I stress again, there's a lot of math in the course, there's a lot of algebra in the course, and rather differential geometry. So a lot of problems are given here. Many of the problem sets Asaf will give are taken from here. If you look deep enough, you will also find solution books, but it's of course meaningless to copy answers from a book. It's also useless to copy answers from other students, because you really have to practice, okay? It's like learning, it's like elementary school. If you don't do it, you can't cheat. You will fail. So use the problem books to find more problems, to train yourself. You will need this training. Bernard Schutz has his book, A First Course. A First Course in General Relativity. This is from 1985. Again, a very nice introductory test. If you get lost on something, especially the early stuff like energy momentum tensor, that's a good resource. There is Wald's book called General Relativity, 1984. This includes some more advanced topics like black holes, global structure spinners. Not all of that we will be able to fit, or most of it we won't be able to fit in this particular semester, but it does have some advanced topics. And the Bible is called MTW, or Meisner, Thorne, and Wheeler. This is from 1973. It's called just Gravity. Or gravitation, rather. Gravitation. This is a book that's about this thick. And the running joke was that it's called Gravitation because it has its own gravitational field. Basically, it has 3 authors who couldn't agree on how to write it. So they wrote 3 books in one. And you get different perspectives when you read it. This type of math and this type of math, and everyone kind of gives their own interpretation. Basically, everything known about GR up to 73 is in this book. They all appear in the library. We have copies here. The library is now at the chemistry building. Asaf and me also have copies of most of these in our own libraries in the offices. It is highly recommended to follow the course with at least 1 book and with the lecture notes that are also available from Asaf on the Lambda. Okay. Questions up to now? Okay, as you can see from the book titles and the topics they cover, general relativity is a physical theory. It's relativistic, by Einstein, of course. And it basically concerns the relation between gravity and space-time and geometry. It is a geometric theory of space-time. From special relativity, you remember that space and time are actually connected and related in what we call Minkowski space, or Minkowski space-time, which was flat in the geometric sense. GR will talk about how we curve that. That's most of this course will be explaining what I just said, explaining the geometry of space-time and why space-time, how we calculate things in the geometry of space-time, or generally in curved geometries. Understanding the physical connections to masses and objects and energy and things like that. And then solving specific problems that we know or situations that we understand. Vacuum, a black hole and Schwarzschild solution, cosmological solutions. All of them will basically follow from the main point of the course, which is Einstein's equation, or Einstein's field equation. So about half the course will be building up to understanding this equation and understanding how to write it, and then the second half approximately to understanding specific solutions. Okay, that's the introduction and admin. Any further questions at this point? Okay, so let's start. We start with special relativity. And a quick reminder. For historical context, 1905, was Einstein's special relativity. Special relativity. And here in 1915 will be general relativity. So today we're going to talk a bit about how Einstein got from here to here. Okay. So special relativity is, of course, about understanding transformations between reference frames. So we have one reference frame, O, or S. Let's see, which one does the stuff use? O. O and O prime. And they have some velocity V between them. Say O prime relative to O. And so in Galilean transformations, we would just have that any velocity U prime in this frame reference is transformed from this one by adding V. This, of course, fails if we get close to the speed of light. We have to replace this Galilean transformation by a Lorentz transformation. Lorentz. So this is Galilee, and this will be replaced by Lorentz transformations. We'll get a little later into the mathematics of it, but just to remind you, what Lorentz transformation does is three things. It conserves the interval delta tau squared. So this is what we call the proper time, as delta t squared minus delta x squared plus delta y squared plus delta z squared over c squared. You can also think of this in more natural units. If you multiply by c squared, and you get here c squared delta tau squared as t squared minus x, y, and z squared. This is the Euclidean part, and this is the Minkowskian part. You will note that the way this is written is opposite in convention to how we had it in special relativity, where we, I'll remind you, usually wrote the minus here, and the plus here. Yes?
It's delta tau all squared, not delta tau squared.
Yes, all of these are in parentheses. Yeah, you have a vector connecting two points or events in space-time, and then you take basically the norm of that displacement vector, and that norm is plus or minus, depending how you define it, the proper time squared. So this is conserved. It's the extension of the Euclidean norm of a vector to the Minkowski norm of a 4-vector. Okay. This is number one. Number two, the limit for V much smaller than C reproduces the Galilean transformations. So the limit is Galilean. This, of course, is crucial observationally, because in our everyday life, we usually see this. So any theory whose limit in everyday circumstances would have been different than what we know experimentally in everyday circumstances has to be ruled out. So this is, if you want, the correspondence principle. And number three, which kind of explains historically how Einstein got to this point, is that this is consistent with Maxwell's equations. If you want Maxwell's electromagnetism. The symmetries of Maxwell's equation manifestly conserves this transformation. It obeys the same symmetry, this Lorentzian symmetry. So this, of course, is a great accomplishment in 1905. What are the problems with special relativity? The first is, going even earlier, from here to here, we always describe the transformation as going from one inertial frame to another inertial frame. This was an inertial frame O, and this was the inertial frame O prime. And we now have to go from one inertial frame to another inertial frame. If they have a relative velocity that's constant in direction and magnitude. Nothing here tells us what is the first inertial frame, or an inertial frame. How do we know if this is an inertial frame or not? If you give us one, we can go to any other. But how do we find a single one? So problem A, what is an inertial frame? Yes?
Why is this a bigger problem than the Newtonian physics?
It is a problem in Newtonian physics. In fact, this question was raised already by Newton. And we'll talk about that in a moment. Yes?
But there's a solution there. There's forces, there's new forces that arise. And
So we'll talk about Newton's answer, and we'll talk about Mach's answer, and then we'll talk about Einstein's answer, which itself is a major step in building GR. But yes, it's definitely a Newtonian problem. If you want to think a bit in the more historical context, Aristotle and Plato and all those guys didn't need this inertial thing because they thought that there was one ideal rest frame. But everything wants to slow down and reach its final point. Galileo and Newton corrected that by saying that the natural inertia of things, or the natural tendency of any object, is not to reach its rest state situation, but to remain in constant motion in a constant velocity. So they extended the rest frame to any inertial frame, which are all equivalent, basically. That prompted the question, okay, so which is the inertial frame? We're stepping further and further from Aristotle as we go and generalize the frames of reference in which we are willing to do physics. And you can kind of already see that this generalization process is what's going to leap us from special relativity to general relativity. It will be another generalization in what frames of reference we're discussing. So that's problem A. And problem B, not surprisingly, will be gravity. More accurately, the instantaneousness of gravity. Right? Because Newton's law of gravity says F equals G m1 m2 over r squared. There's no time here, and there's no answer to the question, wait a minute, if I knock out the sun or make it disappear or hit it with a comet or a black hole and throw it out of orbit, when will the Earth notice it has to go in some different direction? That the gravity source has changed. According to this, it should happen immediately, instantly. There's no time delay here. This, of course, is a problem for Einstein, who had just told us that there's special relativity, there's a limit on velocities. That's the speed of light c, right? Speed of light c here. Nothing can go faster than that, not even information. So this has to be wrong. Okay. If you want to make it even more complicated, you can add the directions here. It's not. I don't even have to move an object or change its distance. Even if I just have two objects circling each other, so that the direction changes, Newton tells me they would instantaneously have to change the force and acceleration and motion based on each other's instantaneous position. And well, Einstein tells us that cannot be. Nothing can be instantaneous. Now, you'd notice again that Maxwell's electromagnetic theory features prominently here. And that's because this thing is, of course, analogous to Coulomb's force. I'm going to put it as Fc here. I'm going to put a little n for Newton here. And at leading order, Coulomb's force was k q1 q2 over r squared. And we already know from Maxwell himself that this is only part of the story. It's almost a fourth of the story. Right? This is derived from, or can be used to derive, Gauss's equation, Gauss's law, which is one of the four Maxwell equations. Two of them have a d to dt term. Right? There's either E or B, but there are terms which do put in the time derivative in Maxwell equations, two of them. And of course, you remember that together with all four Maxwell's equations, these time derivative terms will eventually give us the propagation of electromagnetic waves and the speed of light. So there's some field theory with E and B, which are not present here. E is implicit here, but there's an explicit writing of things with E and B that is a local theory. At every point we can have a relation between the fields and their derivatives and their sources. And from that we get, in the static limit, Coulomb's law, in the wave limit or in the wave situation, propagating waves with velocity c. If I move a charge here, you know when any other charge will feel it. It will be at a delay of the distance between them divided by c. That's the time it takes the information to propagate as an electromagnetic wave. So Einstein is looking for something similar in gravity. This can only be a part of a story. Those are the problems with special relativity. It doesn't tell us what systems it's talking about, and it's missing a key feature of the story, which up to Einstein was no problem, because Newton believed information can travel instantaneously. Now that Einstein has made the speed of light the absolute limit, nothing static at a distance, this is called an action at a distance, nothing like this can survive Einstein after 1905. Yes?
Okay, so if I look at these two equations, they're similar, right? So in the case of an electric force, there is the magnetic force.
Yes.
What if in the case of a gravitational force, you can do something similar to kind of correct it? Kind of like a magnetic force, but analogous and its gravitation.
That's an excellent hunch. Einstein tried that. That was basically the second thing he tried. The first thing he tried was to find some relativistic generalization of something like the scalar potential. But you know you can integrate this to have some potential of gravity, and you can say that F is minus the gradient of phi. Right? You integrate a force, you get the potential. This is a central force. It's always in the direction of the separation between the two bodies, so you know it's integrable, and it can be derived from a potential. So we tried to look at something that would look like this, having a special relativistic consistent formulations of some scalar potential. That didn't work. So the next thing he tried was a vector potential. This is similar to what you might have seen in electromagnetism, or how many of you have already done electromagnetic fields? I think it's the third year course or something. You're doing it now. Okay. So maybe in EM you found that sometimes you can define the vector potential in electromagnetism. Right? You can have some rotor or curl of some field A. This would give you B. Right? Who has seen this? Who has not seen this? Okay. So then you have the electrostatic phi and the magnetic vector potential A. You can pack them together as a 4-vector, A mu. So we're doing relativity, everything is 4 vectors. You can also pack these together. Who has seen this? Okay, in which course? Elementary particles. Okay, so usually you find it either in elementary particles or in E&M theory third year. Sometimes in analytical mechanics, you find the gauge transformations. Okay, different people see it in different places. We might talk about it more in this course. That was the next thing Einstein tried. he tried to define something like this for gravity. Manifestly covariant, right? It's in the proper relativistic form. It's analogous to electromagnetism. That also failed. The failure here can be explained quite easily. If you go through the work, and you'll probably do it later in the course, or in E&M, of writing the action and the energy, you find that the phi squared term and the a squared term have opposite signs. Basically, one of them is like a potential term and one of them is like a kinetic term. If you have like a t minus v term in your Lagrangian, or if you want to write your Hamiltonian. And because electromagnetism is repulsive between like charges, and gravity is attractive between like charges, you get that the action and the energy here basically look the opposite sign to electromagnetism, which means you have infinitely negative energies. But for an electrostatic configuration, or even an electrodynamic configuration, you have a zero state, or a lowest energy state. And then you can go as high up as you want. If you did that for gravity, you'd have the exact opposite. You'd have a cap on energy, and you can go infinitely low, which makes it completely unstable. The system can always decay to lower energies, and so that's not physical. So he ruled that out. And he had to look for something that's not a scalar and not a 4-vector. So what's next up? A tensor. And that would indeed be a tensor theory. It still took him a while to realize what that tensor was. And this will tie us back into the questions of geometry. Okay, so those were the problems with special relativity. And now we're going to have to talk a bit about geometry, how geometry relates into this, in particular how it relates to the first and second questions. So we're now forgetting for a moment about Einstein, and we're going back to Newton. I'm going to leave that 1915 GR here. But now we're going all the way back over 200 years. To around maybe 1690-ish, plus minus 5 to 10 years, with Newton. And as you accurately said, Newton replaced the Aristotelian view of a rest frame, a preferred system, with any number of inertial reference frames. And then he had to ask himself, is there an inertial reference frame? And as someone also mentioned, what you learn in mechanics is that if you leave an inertial frame or transfer to a non-inertial frame relative to an inertial frame, you get fictitious forces. Right? If you stand in an elevator and it starts going up, momentarily, when it's accelerating, you feel pushed to the ground. When it then brakes, you kind of feel yourself elevated to the top. That's a fictitious force, which is basically minus m, too many squiggly lines, minus ma. This will be F. Did you give this a name? Demoivre, I think, or D'Alembert or Demoivre. We can put an F here for fictitious. So of course, this is what happens in the linear acceleration. And if we have, for example, circular motion, or rather, if you want to change from an inertial frame to a rotating frame, you get two fictitious forces. Exactly. You get minus m omega squared r. This is kind of maybe the quickest analogy of this, if you consider the centripetal acceleration.
This is like, oh, not the distance from the axis, not from the force.
Yeah, so I was assuming here a planar motion, but sure, if you want to have it more complicated, the radial distance from the axis perpendicular to the axis. But then, of course, you also have twice m omega cross v. And I'm going to put a plus minus here because I don't remember if I put this in front or this in front. This is the Coriolis force, fictitious forces.
There is also some third force, I think, that has to do with angular acceleration.
Yes.
Like the oil forces.
Yeah, we can go further if we want to complicate what is constant in going between these two frames of reference. But we get these fictitious forces, which Newton already knew about. Then we have, and notice they're all proportional to the mass. This will be kind of crucial. The reason they're proportional to the mass is because Newton tells us in his second law, F equals ma. So if something is a geometric effect from changing frames of reference, the thing that we should be talking about is really the fictitious acceleration, minus m omega squared rho plus minus 2 omega v, without the mass. The mass should cancel out in any fictitious force. If you want to frame it in terms of a force, you then have to basically artificially by hand multiply by the mass. And I'm going to make a slight abuse of notation here, and I'm going to label all of these masses mi. Okay? The inertial mass, which might be how you define mass in mechanics, right? Mass. Who remembers the definition? How did you define mass in your first semester in first year?
Resistance to acceleration.
Resistance to acceleration, exactly. The response, the thing that determines how much acceleration a force will give, or how much force is needed to apply some acceleration. This is the inertial mass in our language. It describes the inertial characteristics or relation between a force on an object or a particle to the acceleration it will experience. And so obviously it will feature in all of these fictitious forces, which are basically saying that we have to account for the particle's acceleration or fictitious acceleration if we go to another reference frame. This is to be distinguished from that little equation we had here before, F Newton, G m1 m2 over r squared, which I'm now going to quantify with a little g, the gravitational mass. Yes?
Not one of the כאילו אחד וקטור השני סקלר.
Okay. This equation stands out as having the mass play a different part. It plays the part of a charge. It plays the part of sourcing a field or a force. And for Newton, there is no a priori reason that this and this should necessarily be equal. Okay, you could imagine, maybe, one could at some point imagine, that different types of materials will have a different relation between their gravity usefulness, or how they source gravity, and how they react to a force. And we'll talk about that a little later. But for now, we'll just have this m inertial in all the fictitious forces, which again Newton knew about. And so now Newton asks, what is the correct reference frame or inertial frame where there are no fictitious forces? How do I know that one should exist? And he started an experiment. So this is called Newton's bucket experiment. The experiment has 4 stages. The first one, you take a bucket and you fill it with water. The bucket is stationary. The bucket has some handle and some string. It's stationary, the water is flat. Now you slowly start to rotate the string. for the handle.
What do you mean slowly?
You start slow and then you can do it fast, but basically you don't. You give it some time to react. Now what happens is that at the beginning, the water is still flat. It takes time to react to the rotation. But then very quickly you find that the water, in one language you can say that the water relative to the bucket is experiencing a centrifugal force, or rather changing from the system of the earth, of the ground, to the system of the bucket. We now have a rotation, so we have a centrifugal force, so the water is pushed outwards, and because it's dependent on rho, the force is stronger the further away from the axis of rotation. And so you get that the center point is basically still stationary, but the other points get pushed towards the bucket, and so you get kind of this parabola thing forming. And if any one of you doesn't have a spare bucket or doesn't want to waste water, you might have done this experiment with a glass of tea, when you use a spoon to twirl it and have the sugar melt inside.
But then you make it like a vortex.
If you do it fast enough, you'll get vortices, yes. That is for a course in hydrodynamics. But if you do it slowly, so the flow is regular, everything is easy, then you get this you can get this parabola shape while you spin. Or instead of spinning the spoon, you can spin the bucket. Now the water is basically being twirled around by the edges. Right? There's friction between the edges of the bucket. It's causing the water to spin. As they spin, you get a profile of velocities, and you get this kind of parabola shape. Okay. Now what's going to happen is that we stop the spinning. If we immediately, at one point, instantaneously stop the spinning of the bucket, what happens to the water? They'll still maintain this shape. They'll still be rotating, but now they'll be slowly slowing down until eventually we get back to the way we started. We get back to flat water. So what Newton is now telling us is, look, here for a while there was no motion, yet the water knew how to get back to the correct shape. We started in something stable, flat, we ended up in something flat. Obviously, these are the fictitious systems, these are the non-inertial systems, and we will single out these. The water knows somehow, right, that between here and here, no force is being applied from outside. We're not spinning the bucket anymore. The water somehow knows how to get back into the flat position, the flat status.
There is a force, there's friction.
Okay. How will we deal with that? Well, there was friction here, right? That's what caused the motion to begin with.
Friction in the opposite direction, something like that.
Yeah. So this will be not kinetic, static friction, right? For example, you want it to move with you. But the argument here is that when you stop applying it, it won't end up, for example, in some other stable state. It has to end up flat. Yes.
When you, in the third part, you hold the bucket still, or you just stop it?
No, if you at the end okay.
Because if you hold it and
if you have slushing, you'll have some angular momentum exchange between the water and the bucket.
So you hold it, or you let it slush?
In Newton's terminology, it doesn't really matter, because at the end, it will always reach this point. Okay, so Newton is telling us there is a preferred inertial frame.
But it doesn't conserve angular momentum. Because in the third part you have angular momentum, in the fourth part you don't.
Okay, so both your point and your point bring us to the next kind of answer to this question, which is given by Mach. Mach is, do I have the year listed here? Okay, sometimes later. This is something like 1905 or 1903 or 7. Ernst Mach. And Mach is kind of playing on this, these intuitions that the water doesn't just know where to go. There is something that has to be conserved. There has to be friction with the bucket. There has to be angular momentum applied by this friction between the water and the bucket. But then, where does the bucket transfer the angular momentum? Where does the friction on the bucket? Who holds the bucket in place? It has to be the person holding the bucket, or the ground on which the bucket is stationary. So basically, you have to look further out of the system. You can't look at the bucket kind of in isolation. You have to ask, what is the bucket connected to? And Mach's answer is the bucket is connected to the earth. Because the earth is so massive, more than the bucket, you hardly notice that the earth is changing its motion, while the bucket stops and the water stops, and really what you should say that this water is level relative to the earth, to the mass of the earth. Mach would go even further and say, wait a minute, what is the earth trying to be stationary with respect to? And you would say the sun. From the sun you would say the galaxy, or maybe all the galaxies and all the stars. So Mach, or the Mach principle, I'm going to quote this so I don't get it accurately. So Mach says, Newton's experiment with the rotating vessel of water, the bucket, simply informs us that the relative rotation of the water with respect to the size of the vessel produces no noticeable centrifugal forces, but that such forces are produced by its relative rotation with respect to the mass of the Earth and other celestial bodies. So Mach is trying to give us an answer, right? This complicated formulation is basically telling us that to distinguish between our inertial reference frame and a non-inertial reference frame, the non-inertial one is the one with fictitious centrifugal forces, you have to look further and further out to all the objects in the universe, basically, the Earth and then the stars. If you kind of average all the mass or the positions of all the system, that will be the correct inertial frame. Every experiment you do will basically want eventually to be stationary or inertial, relative or flat, relative to the universe. The object in the universe, the mass in the universe. Okay, so that brings us from Newton to Mach. Yes?
In the case of Newton's gravity, right, there was this problem that it responded immediately to the change in radius, right?
Yeah, that's our second problem.
In the case of Mach, it's the same problem, because if all the universe vanishes, then there is instantaneous transmission of information.
Yes, that's a problem with Mach's principle. Again, okay, in some sense, it tries to
shove the problem.
Yeah, it tries to shove the problem not underneath the rug, but further out, right?
Kick the can.
How do you say sweep? It tries to sweep the problem under the rug, which is infinitely far away.
It's called kick the can down the street.
Kick the can down the street. Yeah, exactly. Pass on the hot potato. Any way you wanna call it. We'll just move the problem further out to the stars, and if they're stationary enough, then this is no longer a problem. Yes.
Well, I guess you were neglecting the fact that the level of water in the stationary bucket are not really flat, because the Earth is a central force, so same way as the oceans are not flat, then
yeah, but that's
you neglect that.
Yeah,
And
because the bucket is small and the Earth is big, so this could be. I also neglected surface terms. Of course, you know, water is never level.
Yeah.
It's slightly curved at the edges. I'm neglecting that as well.
And if I'm putting this bucket in the North Pole,
Yes.
the Earth is rotating relative to the stars.
Yes.
So when you say we have to compare it to the inertial frame of the bodies around us, you need to put like a weight on the effect of the Earth and the stars. is the bucket at the North Pole is even measurable, the rotation of the Earth? Or you expect it
Well,
to be
depends on
flat?
how,
If you put
again, it depends on how much, so you can calculate the acceleration, the rotational acceleration, and you don't even have to go to the North Pole, right?
yeah,
Because you have
I'm just
cosine
making it
theta.
simple. Yeah,
term.
I'm just making it simple.
Yeah, you can calculate that. You can calculate the difference in gravity. You can even calculate the difference in g by latitude because of these centrifugal terms.
Right.
And people in Newton's age and slightly later already did that. It's
So-
measurable.
You do have to be at the North Pole.
If you are at the North Pole and you're trying to think about whether the bucket will be leveled, if that's measured at all with a slow rotation of the Earth, and so I would say that we need some measure of what is the effect of the close Earth rather against the far stars, which are more massive but much further. Is this thing known?
So there are three questions underlying here. One is the experimental setup, what can be measured and what not. The second, maybe related to that, is do we know to calculate how the Earth is moving relative to the stars around us? And the answer is that yes, today we can, and Newton couldn't, at least not outside of the solar system. But from the 1800s, we can measure motion of stars in the sky and trace them, and we know we call it their motion relative to us, but we can also measure our motion relative to them, and today we also know relative to the galactic center and all that. We can measure that. So that's a second question. The answer is yes, related to the experimental question of how accurately we can measure these effects. But the crucial point here is actually the third one, which is not the details of the experimental setup, but the conceptual experiment. That is there a system which we can call inertial? And if there is one, then we can move from that to any other system, be it geocentric or at some latitude, or even rotating around the sun. We could use a heliocentric system. We can use any. Once we have one, we can transfer between these systems with ease. The question is, can we find one? And of course, you push the can further and further down. Mach is saying, okay, look at the far away, average the far away stars. And now I can tell you anything you want with any accuracy that you want. I can go from the stars to the galaxy, from the galaxy to the sun around that, from that to us around the sun, from the rotation of the Earth. I can calculate any of these things. I just want to know what is real, right? What is the correct system? And Mach says that there is one. It's the one created by all the masses in the universe. Yes?
It might be too wild at this point, but if I know that the entirety of the universe is an inertial system, it should be an inertial system, that allows me to know something about the bucket, which is very far away from there.
Mm-hmm.
That is essentially how entanglement is. You measure a particle here, and the wave function collapses in a faraway place.
Mm-hmm.
It's a similar situation. You know the final state of the bucket by measuring the rest of the universe and saying, well, this is an inertial frame. Also, if the entire universe had some total angular momentum relative to something else, then you could know that by seeing that the final state of the bucket is not that in a hypothetical situation. I feel like I'm connecting things.
Oh, yeah, I'm going to leave the quantum discussion out of here because Einstein would have liked it that way. But yes, the essence here, and the thing that troubled Einstein with entanglement and with quantum mechanics, is precisely this seeming violation of this no action at a distance principle. Einstein wanted things to be local and transferred at the speed of light. Now I won't get into the question of whether quantum mechanics and entanglement actually is an action at a distance. That's for your quantum mechanics courses. But definitely the troubling point for Einstein there was that it seems to violate this simultaneity problem. Yes?
From what Mark concluded, can we say that the inertial mass equals to the gravitational mass? Because the first stuff is because the inertial mass.
Mach didn't say that. That's not in the principle. That's going to be, and the next thing we're going to be immediately, the equivalence principle, which literally is showing and assuming or measuring the equivalence of mi and mg. That will be the Etwish experiment, which we will get to in about 30 seconds. Yes?
No, the biggest problem is that he's basically saying the laws of physics are completely going to change if some planet somewhere vanishes or a new mass comes into the universe or close enough to. The laws of physics all have to change all of a sudden because the definition of an inertial frame is going to change immediately.
Yes and no. First of all, one can say that mass can't just appear from out of nowhere.
It could come closer or something. So in a low,
Yeah, but on the average, you have conservation of linear momentum, angular momentum, and total mass in the universe. At least at that time, they thought they had that. So that's not a real. That's a conceptual problem, but it's not one. But it's one that he could easily argue away. Right? These things are conserved, and so the center of mass of the universe, if you want, in his terminology, is constant. The velocity is constant, and momentum. All these things you can kind of assume that they're fixed. And this is, of course, one of the motivations for the Mach principle, because as we said with the friction or with the angular momentum of the bucket, you look further out, it has to be conserved somehow. If you look at the largest system you can think of that conserves what you expect to be conserved quantities, that will be your correct fixed reference frame. But yes, of course, if things change, if some mass appears out of nowhere, it doesn't appear out of nowhere. If some masses change direction, or if something happens, maybe you could think of something to violate this action at a distance, and it might take time, and that's the problem.
Just in principle, if you have a chemical reaction, something that's not just physical objects moving around, all of a sudden the laws of physics have to change.
No, that's not a problem. Chemical reactions conserve mass and energy. Okay, you might have to generalize the Mach principle to say energy and not just mass.
Which doesn't make sense at that point, because it's all based on calculations of mass. It's based on how masses are moving around. That's how you define the inertial.
Okay, so you have an underlying assumption that energy doesn't gravitate, only mass gravitates, which you can kind of interpret from here. I agree. In Newtonian terms, energy doesn't gravitate. In Einstein's terms, it will. But indeed, since we're still in before 1915, you can consider that a problem with the Mach principle, if you want. So these together with one other principle will lead Einstein to the solution of general relativity, of geometry as the main thing. I'll just say that Einstein took from the Newton-Mach debate, if you want. Okay, Newton had been dead for 200 years, but from these physical debates across the centuries, he took from Mach the importance of mass. So masses will affect basically the geometry or what you want to define your inertial systems. And from Newton, kind of this notion that once you have a system, it no longer matters what the masses nearby do for the purposes of inertia. The intermediary between these two will be positing or describing the geometry of space-time. In Einstein's gravity, the masses and energy and other things will dictate the geometry, and then in a geometry, every experiment will basically be equivalent to the same experiment in any other reference frame. So from Newton's concept of inertial frames being interchangeable, you can do an experiment in one, do the experiment in another, and expect the same results, independent of how the observer chooses to define its reference frame. Einstein generalized that to talk about frames that are not necessarily inertial. But with a caveat, the non-inertiality will in some sense determine the geometry, will be determined by the masses, that will determine the geometry, and then you can carry experiments in any one of those frames of reference. Okay, a crucial point in doing that was relating the inertial mass to the gravitational mass. So here we have an experiment. So we'll delete this. This is an experiment called Eötvös experiment. Eötvös was a Hungarian scientist working in Budapest. I don't have the year here, but that doesn't matter. And the experiment goes like this.
According to Wikipedia, 1885.
1885. Can you find the year for the Mach principle?
Wait, this is.
The Michael Morley, maybe?
Michael Morley was
1887, yeah.
Oh wait,
Okay, you look for that. Meanwhile, I'll describe.
in 1922. Sorry, this is Eötvös.
19?
In 1922. 1922.
Okay, we'll fill in the year later. The principle here is to measure mi to mg, or rather the ratio mi to mg. Are they the same? So to do this, Eötvös needed to construct an experiment that can distinguish between these two types of masses. And this is difficult to do, because if you recall, if you drop things, they drop as, you know, m1g will be the mass of the Earth, m2g will be the object, and as Galileo tells us, everything basically falls at the same acceleration, because you can this is linear in m2g. So distinguishing between mg2 and mi2 is tricky. So what did Eötvös do? He took a rod, of a light rod, so we're not going to concern ourselves with its mass. And here you put a large mass m1, and here you put a large mass m2, and you want to keep the rod stationary, so you have to somehow balance the masses on both sides. You have a string somewhere here, and they are free to, the rod is free to rotate about this point in any direction. And we want to balance it. So far, kind of like what kids do in a playground. They find a seesaw and they try to balance each other out. But now we remind ourselves that the Earth itself is moving. And that unless this experiment is done at the North Pole, there will be some angle here to how the Earth is positioned. So if this is the Earth, in Budapest here, something like, I don't know, 50 degrees north, this will be the down direction, which here I can represent this way as gravity. This will be F1g, which is mg1 times g. And here I'm going to have F2g, which is mg2 times g. G is 9 point whatever gravity. This is the direction of these forces. I also have the centrifugal forces, because this is the axis of the Earth, and this whole experiment is rotating. And the direction of the centrifugal force goes out to here. This will be Fc, the centrifugal force. Yes?
You assume the Earth is completely round.
I don't have to assume the Earth is completely round. I can do it in any latitude, and I don't have to assume roundness. Okay. For completeness, I also have a tension T here. I'm going to put Fc in some direction. Okay, this is not necessarily only up and to the right. This can have X, Y, and Z components, because I didn't specify the orientation of the rod connecting them. It could be like this, it could be like this, it could be basically in any direction in the plane perpendicular to the down direction. Okay? I'm going to have it mark this angle here as theta. Make sure I get all of these correct. Let's put a system of axes here. So we'll mark this as x, this as y, and this as z. And we'll explicitly make it not this direction. So this will be z. So these forces, I'm going to call them F1 centrifugal and F2 centrifugal. I don't care. I don't care.
Is it rotating?
I'm not doing any cross products. Yeah, I'm gonna ignore it. Okay, I am doing cross product, so we'll change the axes. Let's do x, y, and z.
Is it
Now it's a right-handed system. Yes.
Is it rotating with the rod, the x, y, and z, or it's stationary and the rod rotates inside the system?
So we're going to reach a point where this. We're going to try to balance this. So these will not be rotating around the axis. But all of this is rotating around the Earth. Okay? There are two possible rotations here. One of them we can't avoid. The Earth is still rotating. But we're going to try to stop this from rotating. We're going to keep it level. Okay. So now we have the radius of the Earth, r. And to keep the system balanced or stationary, we're going to have to balance two things. One of them is the forces acting here, and one of them is the angular momentum, or the torques. Torque is, in Hebrew, moment koach. Right? We have to balance the torques about this point. So let's do that. Let's calculate the total torque. Has to be 0 about this point. So let's calculate component by component. Starting with tau z. Tau z has to be equal to 0. Which torques are going to contribute to the z direction here?
Only the centrifugal. Only the centrifugal.
Right. Wait, why?
Because the gravity is
Exactly.
Z
Gravity
direction.
is parallel to the z direction. The tension T is both parallel and goes through this point. So both the, right? You all studied torques in mechanics, right? Okay. So tau is R cos F. So for this one, this is parallel, and this is parallel, and for gravity, this one's parallel. So the only possible torques we're left with, in the, how did I mark the z direction again? I think I used different. Okay, we'll just do it.
Draw the arrows in the other direction.
Okay, so we have M1, mg1g times, let's call this R1.
That's in the z direction. But you said but that's not
This is a force in,
it's in the x
yes.
direction.
This is the x direction. This goes like this. Okay, so we're going to have Fm1g in the x direction times the displacement in the y direction. So we're going to have a torque. This goes this way. This will be in the opposite direction. So we'll have minus mg2g times r2. And we will have components of now we'll have components of the centrifugal force. So here we have a general direction, or rather we want to have the x component of this times this distance. So let's say it goes, okay, we only want the up component, right?
It's two-dimensional.
This component will be alongside x, so it's 0. The x component this way will be parallel to x, so I only want the up component of the centrifugal force. You have a hand up? No. Okay.
You assume that F1C and F2C is parallel?
Yes, because my experiment is small, and they're both pointing away from the axis of the Earth. So I'm going to have now the opposite direction here. F1C is going to be m inertial 1 times omega squared r sine theta. Sine or cosine? Let's see. I want the up part, probably both. So, yeah, cosine theta. And I'm going to replace this r by this rho. I only actually care about the radius in the plane of the rotation. Okay, so this one is basically this component going up. So it's rotating. This is doing r times z. I'm getting that direction, opposite to this one, which was pulling me down. And same for the other one, plus mi2 omega squared rho cosine theta. What?
This is a minus because the R is in the opposite direction. This is only
This-
the force. This is only the force, not the torque.
This is a minus.
You didn't-
I'm going to add an R1, and I'm going to add an R2. Now, these are opposite in direction, and these are opposite in direction. Okay? Okay. So that's the X part. Now for the Y part. For the Y parts, I want, okay. So obviously both this R and this R are along Y, so there's no Y part. We'll write that explicitly. Tau Y equals 0. And now, tau Z. What's going to cause rotations about this axis? It's not going to be gravity on either side, because that's parallel. So I'll only have the component of F1C and the component of F2C.
in the X direction.
Their components in the X direction. So now I'm going to have, again, mi1 omega squared rho. Now I'll have probably a sine theta. From one side, r1, and from the other side, mi2 omega squared rho sine theta r2. Okay, so gravity comes in here, and the rest comes in here.
Question.
Yes.
Why is it rho cosine theta? If rho is the distance from the axis, it should be 0.
So this is what causes the, if you want the magnitude of the centrifugal force,
Yeah.
it's this squared, it's rho omega squared, but it goes in this direction. And I only want a component, okay, for one of them I want this component, and now for the other I want this component.
You assume there is
Which
no component
direction
in
is
the
it
Y
from?
direction. Because
I can do that. If you want the y direction, I can add another sine phi here, if you want. But that doesn't really matter because this is equal to 0, and what I'm going to do now is divide between them. And I'm just going to find that what every child learns in playground, this, and this cancel out. and we get mi1 r1 equals to mi2 r2. So you can do it as complicated as you want, but basically this is, and again, this is where the historicity of the Earth will also cancel out. All you need is this. Okay. So now we're going to plug this into here, and let's simplify it a bit. Let's isolate everything about 1 in one side, everything about 2 in the other side. That's a fair first attempt. Okay. So we have mg1 g r1 minus r1 mi1 omega squared rho cosine theta equals gmg mg2 r2 minus r2 mi2 omega squared rho cosine theta. And we have this equation, which is telling us we can replace R2 by mi1 r1 over mi2. So we'll plug that here. We'll have g mg2 r1 mi1 over mi2. Okay, before that, I have R2 twice here. So I'm going to rewrite this.
But the second term is just cancel.
R2, yeah, exactly. G mg2 minus mi2 omega squared rho cosine theta. So now I have this instead of R2, and then G mg2 minus mi2 omega squared rho cosine theta equals R1 G mg1 minus omega squared rho cosine theta. Any arguments or mistakes I might have made thus far?
That rho cosine theta, right? It's like in the spherical coordinates that is cosine
The units isn't right.
cosine phi. So
Yeah.
the cosine phi should also cancel out, right?
Yeah.
The unit isn't right in the right direction. You need to add the m.
The mi1, of course. I need to add mi1.
Actually, no. Actually,
So this is dimensionless. Radius and radius. In fact, I'll cancel them out. And now I have force, 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 force. Yes.
yeah, rho should still be the radius of the Earth.
It's the if you want it's r sine theta itself, right? It's the radius of the circular orbit at whichever latitude we are on. If we're not on the equator, it's not exactly the radius of the Earth. It's r sine 50 degrees north or something like that.
In spherical coordinates, that if you say that x is r cosine theta cosine phi, then that r is the radius from the origin, and the origin is different from here.
It's the radius.
But this cosine theta doesn't come from there. This cosine theta comes from looking at the z component of the centrifugal force. It comes from this theta.
Oh, the theta is that.
Yeah. which would be the same, right? It would be the same as the one for the center of the Earth, because, again, if you have this, then this angle is equal to this angle. So they're both sacred. Okay, so now we have this ratio. Here we can cancel out. Let's do that. What am I going to get here? Did I make a mistake, a calculation mistake?
You can just drop the
ratios
second
are
term
the
on
same.
each
What?
The ratios
side.
are the same.
Hmm?
You get that the ratios.
Which ratios?
The gravitational and the inertia. mg2 divided by
I2?
I2 equal to mg1 divided by mi.
That's what I want to get.
If you take out the masses from the
You can
Let's
cancel out
divide
the
by
second
mi1. Good, let's divide by that.
And, you can
And here we'll
cancel the
have,
second term.
so we'll have here g, mg2 divided by mi2 minus omega squared rho cosine theta. I divided by mi1, so now I'll divide the right side by mi1. G mg1 by mg2 minus omega squared rho cosine theta. Now this and this cancel out. Then g as a constant cancels out. And I finally get what I wanted. So Edward gets what he wanted. mg2 divided by mi2 is equal to mg1 by m. This should be an I. This should be an I. And I1. So this is a result which we calculate from an experiment.
I1.
This is G1. Oh, yeah, I put it in the wrong place. This is I. Okay, yeah, G1 I1. This is an experimental result which we derive if we manage to get this balanced. So if this balances out, then we have an equivalence, inequality in the ratio of mg to mi for the two objects. Now Edwards repeats this experiment with many different masses, made of many different materials, at the different latitudes on the Earth, and it's been measured many times since. We found our way to measure or to compare mg to mi. And in every experiment to date, and today we have, I think, an accuracy of about 10 to the minus 11 in types of Edwards experiments or mg to mi experiments, we always find the same ratio. And once we always find the same ratio, we basically call it 1. It's a constant, we normalize it to 1. If it weren't 1, we could just absorb the difference in Newton's constant g. Okay? So now we know or measure that gravitational mass, the mass that creates gravity, is the same as the inertial mass, the mass that experiences geometry. And this is kind of the missing link with the hint in Einstein's relation of the Newton experiment and the Mach principle into realizing that gravity and geometry are basically the same. The thing that causes gravity has to be geometry, and the masses will be, on the one hand, creating gravity, that is creating the geometry of curving spacetime. And then the same mass will be inertial. It will feel the curvature of spacetime and respond to that geometry or respond to gravity. Questions? Okay, so to be clear, this is called the equivalence principle. You might later discuss various formulations of it, the weak equivalence principle, the strong equivalence principle. In this form, it basically says that gravitational mass and inertial mass are the same. What Einstein's formulation would make of this would be that at every point in an arbitrary gravitational field, that is a geometric spacetime, it is possible to choose a locally inertial frame such that, to whatever accuracy you can actually guarantee this, the laws of nature take the same form as in any other inertial frame, an unaccelerated frame in Cartesian coordinates. Okay? It means you can pack all these fictitious forces into a different geometry. But locally, if the experiment is small enough, you can think of it as an inertial frame. Okay? All frames, so Newton asks which is the inertial frame. Einstein answers, if they're small enough, every frame can be treated as inertial, but the geometry is not necessarily flat. Locally, it would be flat. The global geometry would not be flat. But Mach's principle tells us we have to look far away at larger scales. The overall geometry might not be flat, but it will be locally flat at every point if you look sufficiently close enough. Yes?
Close enough in space or in space-time? Like
Both.
here?
Both. Obviously, if you have if you do an experiment at a single point, then close enough in space, if the experiment is short in time, you can treat it as flat. But if you wait for the Earth to complete a rotation or something, if it's long enough, then you're also exploring more of space. So you need your system to be sufficiently small in space and time, locally. We'll see further along the course that this is sufficiently close in the differential geometry sense. Right? You need to find an environment of a point where everything is sufficiently flat, the derivatives are sufficiently small, and stuff like that.
Like when we are close to maximum or minimum?
Exactly. It's like deriving any curved function you can approximate close enough as basically a straight line. Okay? So locally flat. Deviations from that will be given by the derivatives of that function. So Einstein is slowly hinting to us that masses create gravity through geometry. This geometry will be differentiable, so it will be smooth, hopefully. And at every point, close enough, you have an environment where you can do your regular physics as if you were in flat space-time, as if your system is inertial. Yes?
You're saying that it's smooth. You're making some kind of assumption about what masses look like as well? Like they're not point masses or stuff like that, or it still works?
So, in the context it was derived, probably there was an underlying assumption that the mass distribution itself is smooth. We'll see later in the course that this is typically a good assumption because you don't find masses infinitely dense. Unless, for example, you have a black hole and then you have a singularity in space-time with all the problems that would entail, including, first and foremost, a breakdown of general relativity. General relativity will assume a smooth and enough times differentiable space-time geometry. And because it will tie this space-time geometry to the masses and energies and whatever matter is creating this geometry, it will also implicitly assume that all of those are smooth enough. If not, another set of problems, not all of which we can solve. Okay. Questions up to now? Again, we have now we are hinting or building towards a geometric explanation of gravity. It will remain to be seen how exactly masses create this curvature. That will come in the Einstein equation. But before we can get there, we have to find a slightly more robust way of describing curved geometry mathematically. It's fine just to say things are curved, but now we actually have to define our functions and start differentiating them. So that brings us to today's fourth topic, which is Riemannian geometry. And I'm going to strongly offend the mathematicians in the room and slightly offend the historians in the room by breaking the history of geometry into 3 stages. I'm going to call them Euclidean geometry. This is what you learn in high school, or I don't know, elementary school, or whenever you learn about triangles. What's the most important thing you know about flat triangles in Euclidean space?
Some of the angles.
Sum of the angles is pi. Okay? This is in fact, if this is everywhere true, space-time is flat. It's an if and only if. If and only if every triangle's sum of angles is exactly pi, then space-time is flat. Or space is flat. There's not even time here. I'll say that in the time of Einstein, there wasn't yet, in special relativity, there was not yet Minkowskian space-time. That kind of was an answer to Einstein, but we'll leave that aside. The next step is going to be Gauss. This is what people usually think of when they think about non-Euclidean geometry. So this is in the 18th century, and basically it says, we don't have to assume that. That doesn't have to be true. We can think of perfectly fine surfaces which do not obey this geometry. Which is the most famous one?
Sphere.
Hmm?
Sphere.
A sphere. We live on one. Okay, this is a sphere. And I can easily find a triangle whose angles do not sum up to 180 or to pi. Let's take, say, a point here in the Bay of Guinea, 0, 0. Go all the way to the North Pole. Take a 90-degree angle. So I'm going to go down now at 90. Where does 90 come out to? Probably around here. Back to the equator. But make a 90-degree turn. Go west along the equator, back to the Bay of Guinea. I've already covered 180 degrees, right? 90 at the pole and 90 at the equator. Now I'm closing up on my triangle, and that's another 90-degree angle to go up to the North Pole, between the direction west and the direction north. So I have 270 degrees covered in this portion in this triangle. Conclusion, the Earth is not flat. Tell that to your flat earther friends. The Earth is not flat. And in fact, Gauss has this theorem. I think this one is called the Tyrol gradient, but I'm not sure if it was indeed this one. But that says you can calculate the curvature. If you have a constant curvature for the first stage, the sum of angles minus pi will give you basically a constant times the constant curvature of the spacetime. In a sphere, it's positive. We have an excess angle. The triangle is more than pi degrees, or pi radians. You can have constant negative curvatures, which is what happens if you look at a hyperboloid, for example. And then the angles will always sum up to less than pi. So let's have this kind of sphere here, and we had the equator, and we had this going north, and then down. We had 90, 90, 90. There's also the area here. The constant is the area that you encircle. If we had a smaller circle, a smaller triangle, for example, if we had something like this, these angles, suppose it's an equilateral triangle, these angles always now have to be smaller than 90 degrees each. In Gaussian curvature, the area times the constant curvature is equal to the excess angles.
I think you have a constant also.
This is a constant curvature. This is a constant positive curvature. It's like 1 over the radius or 1 over the radius squared. Probably 1 over the radius squared. And if you integrate it over the surface area that you're covering, in this case, this is 1/8 of a sphere, which is 4 pi is the sphere. If you divide it by 1/8, you get half pi. And that's exactly the excess angle, because we have 3/2 pi rather than 1 pi. Here the area is smaller, and so the excess area is smaller, the excess angle is smaller, and so you can get that these angles are getting smaller and smaller. And of course the limit of this, if the triangle is really small, will be what?
0.
Flat. Right? That's, if I draw a triangle here, it's on a sphere, but the area is small relative to the radius of the sphere squared. There's very little excess area, or encircled area, very little excess angle, and so we get the limit of flat space. So this is for the simple case of constant curvature. And then we have Riemann. And Riemann defined more complex geometries, basically defining a function dxy called the metric. It will now give us a metric which itself doesn't have to be constant. It can depend on different points in our space or surface or space-time or whatever. And we will distinguish between internal curvature and external curvature. The metric gives us distance between 2 points. It can be flat, even if we have external curvature which is not flat. I'll give you an example. This sheet of paper is arguably flat. Does anyone disagree that this is flat? Okay, I can draw 2 points on it, and a line, and I can draw any triangle that I like. What will be the sum of angles? 180. It's flat. Now I can take this sheet and I can curve it, for example, into a cylinder. What is now the sum of the angles?
Still 180.
Still 180, because it's the same angles. I didn't change any internal angles. I didn't change any internal distances. The space here within the sheet, the two-dimensional metric describing this sheet of paper,
The curvature is still 0.
is still flat. The curvature is still 0. This sheet only has external curvature. It's a two-dimensional sheet curved in 3 dimensions, but not in 2 dimensions. The metric is the same as flat space. I can also have a funny cone thing, and I can put on a party hat or a KKK hat or anything you want. I can make a lot of external curvatures without affecting the internal geometry. Yes?
The Gaussian curvature remains 0, right?
The Gaussian curvature remains 0. The internal curvature is not changing. I'm only doing external things. I'm not pulling the sheet. I'm not tearing the sheet. I'm not making any external change.
I think the theoremic argument says that the Gaussian curvature corresponds to the external curvature. So, and that's the thing. I think
We won't get into the math of that
I
right
think
now.
the theorem we discussed earlier, and we said about the sum of angles. I think it's the Gauss-Bonnet theorem.
It could be Gauss-Bonnet. That even sounds correct. This again is a sphere. We know the curvature here is different. It's the internal curvature. It's the intrinsic curvature. That's the correct word. It's not external and internal. It's intrinsic and extrinsic. Intrinsic and extrinsic. What this means is that there is no way I can fold this sheet of paper on the globe and without wrinkle. Okay, it's impossible. You see, try and it always kind of comes out because this is curved and this is flat, and it cannot work. And you can try this at home. I'm sure you have at some point before. You can't make a sphere out of a sheet. You have to either tear it and stitch it again, or kind of curve it if you want it to be consistent. And this is the problem, actually. This is the problem that was discovered way before Gauss and Riemann. This was discovered when cartographers wanted to map out the oceans and put it in a map, and found that it's impossible because it warps the representation. Okay, there's intrinsic curvature here, which we will now, next class or next few weeks, start to define as Riemannian curvature, and we'll describe exactly how these two are different and how one will derive curvature expressions and tensors from this metric function, which doesn't have to be flat. Okay, the last thing Asaf wanted here is to say that, in summary, general relativity is again based on the equivalence principle of inertial and gravitational mass, which implies, or which let Einstein derive general relativity as a geometric theory of gravity, mass curves space-time, and then locally you can do experiments as if you were in an inertial frame, but the metric doesn't have to be globally or locally flat. Well, it doesn't have to be globally flat, and locally we will basically restrict ourselves to things that are locally flat close enough. Asaf will talk about the Schwarzschild solution for black holes, cosmology, which is the metric for the entire universe, its expansion, and we'll get more into the math on Thursday. Any questions? Yes?
So the way you define an inertial system is by saying that it's a system in which the sum of angles of every triangle is pi.
No. So this is maybe misuse of the term. We no longer discuss inertial frames from this point on, because we realize that in some sense, if the experiment is in a small enough portion of space-time, it will always be locally flat. So you can treat it as inertial, but it won't be globally inertial, which is maybe what Mach wanted or what Newton had imagined. You don't have a global inertial system, and now things will only be locally flat. It's the language of differential geometry, or differentials in general. We will do things close enough. We will describe things, or try to describe things, such that they are locally flat. We will find ourselves in a problem when we start doing things on an extended region. There will no longer be, that assumption will break. If you could only do things in flat space-time, it wouldn't be interesting. It's because sometimes we do things that are on a larger scale that weird things start to happen. Maybe we'll start next week by showing what happens to even just a vector when you try to move it along a sphere. It might start pointing up, and now it's pointing to another side, and now it's pointing on the equator. So the vector itself rotated just by moving around different points on the sphere. Because again, it's not flat. So if you have an extent, something is not local, you'll get curvature effects. Any more questions?
It's the same as there is this term, a momentarily co-moving reference frame.
Yeah, exactly. A momentarily co-moving reference frame is something that you want to do locally with something. Exactly. It's like if you have a Taylor expansion around the point, if you move away from the point, it goes back. You need higher derivatives. Okay, good luck. Thursday at 12, right? Thursday, 12. Yes.